right. So up next, DK Panda from Ohio State University.
So good afternoon, everybody. I know I am standing between you and the lunch. Okay. Thanks to the organizers for inviting me here. I think Mark, we were talking yesterday night, except the first one I have been here for every of the other events. I'm very happy to share some of the things what we have been doing over the years. So the talk today, I'll be focusing on like a high performance and scalable middleware for AI, a vendor agnostic approach with MPI-driven solutions. So I'll go into more details and indicate what I mean by that. So if you take a very broad look in the field, like go back 50 years, this is where like scientific computing HPC started. In another 25 years, we had the big data came, compute and data got merged. And then in another 10 years, we entered the AI field. Well, now if you see, what is happening is that the same HPC AI and big data are there, but how the data and where the data is coming is becoming a little bit different. Like the left-hand side is the traditional HPC cluster. Many of you must be familiar. We have the data, file systems. We operate on those. But the right-hand side is the more exciting things. What's happening these days, the data is coming from drones, coming from sensors, coming from medical instruments. And that is called like a computing continuum. And in that context, you need to make sure like your AI models, the big data, HPC, they're not just running at one place. I mean, you have to run this on a computing continuum. Okay, so this is where actually the bigger challenges are coming. So I'll just head into this a little bit. I think in one of the years, I believe last year, the previous year, I indicated there is an NSF AI institute called Icicle. We are doing a lot of things on that side. I'll not go into very details, but the solutions what we are proposing on the left-hand side can be easily migrated to the right-hand side. So the broad goal is how do we design this kind of high performance and scalable middleware while taking advantage of heterogeneous resources. When I say heterogeneous resources, we have CPU, GPU, DPU. Many of you know the data center processing unit like the blue fields and all are coming, IPU. So there is in a computing continuum, you see all these devices are being deployed at different places, and we need to take advantage of those as well as the cloud resource. So while we are looking at the big picture, we also need to make sure like we are providing the solutions which are not just isolated. Okay, and I think Paul indicated this in his talk also. These days, if you take any complicated workflow or a longer workflow, it is not just HPC. You might be collecting a lot of data. You might be doing some big data processing. After that, you do some training, which is like an HPC. Okay, so like this, you are in a continuous cycle between this HPC, deep learning, machine learning, and big data. And then, of course, we need to run these both on the on-premise system as well as in the cloud. So this is where in my group, we have been focusing a lot on called convergent software stack. And I'll go into more details. Because irrespective of whatever you do, like let's say machine learning or any AI workload or HPC or big data, you need both scale up and scale out. I'm sure all of you are familiar. Like a scale up is within the node. You keep on adding more CPUs, GPUs to get better and better performance. But there is a limit. You cannot put like more than 8 GPUs or 16 GPUs. So then I have to scale out. So this is where what we are trying to propose, and that's what I'll try to show, irrespective of like using multiple different software stacks, can we have the MPI, which is like a message passing interface library, as the runtime to get that scale up and scale out. Okay, so if you do that design, then everything runs over MPI. I'll give you a lot of examples. And you don't need like a very vendor proprietary library, I know some of you use it, NVIDIA says, okay, you just use Nickel library. AMD comes and says you use Nickel library. Intel comes and saying you use XCL library. You don't need any of those libraries. Okay, those are only focusing on the collectives. Whereas the MPI library has been optimized over the years for multiple and collectives, one-sided, everything is there. Okay, so that's what I'll try to show some solutions. You don't need any of those libraries, but still get very good performance and scalability. And that's what we are trying to do. So I'll go into like a major 3 parts in the talk. I'll start with this MAPRIDGE MPI library project. Some of you might be familiar, and if not, I'll introduce that. And then those are our base modules. On top of that, we have this ideal project where we have linked Now you can actually run PyTorch, TensorFlow, everything over MPI, okay, without even touching the upper layer. I'll show you how to do that. We have a lot of software modules. Same thing is also on the big data. You can actually run Spark over MPI. You can run Dask over MPI, okay, without changing any of the applications, okay, and this is where you get very good performance. So within MIP's library, so let me just give and introduce the overview and then the Convert software stack. So how many of you heard of this project? Okay, several of you know. So I started actually this project in year 2000, okay. When InfiniBand just came, I am sure all of you know about InfiniBand, right? So when InfiniBand was introduced in October 2000, prior to that, like in my group, we were working on Mirinet, Quadrix, if some of the old timers remember those technologies. And when InfiniBand came, they had the hardware, but there was no software, okay? So I still remember the day I went to Mellanox to talk to them, saying you have an exciting hardware and I know how to design a software. So the person asked me saying, what is your business model? I said, I don't have any business, okay? That's how the conversation started, okay? Literally, okay? And the person is Kevin Deerling, so I think many of you know. But then we had a long partnership with Mellanox, and we had the first software, open source, we actually introduced in supercomputing 2002, almost 22 years back. And I'm proud of my team. We are like coming from academia, we are able to sustain this project for 23 years with not only funding from federal agency, funding from industry, and it is going very strong. And now we actually cover all interconnects, not just InfiniBand, you name any HPC interconnect like OmniPath, Ethernet iWarp, Rocky, even AWS EFA. We have very customized design for that, Rocky, Intel Ethernet, everything. So currently these are being used, this stack is being used by more than 3,400 organizations in 92 countries. So if you go to this website, these are the registered users. You will see the names periodically we update, and a lot of people download without registration. That is also okay with us. So from the MIP's website, now we have crossed almost 1.8 million downloads, just from our website. But it's a part of like Red Hat, SUSE, OpenHPC, Stack. We don't keep track of this. These are the direct things. And then as a part of this project, I think many of you must be familiar, we have an OSU MPI micro benchmark suite called OMB. Okay, many of you might have used it. When we started this project, people knew how to measure the application level performance, but nobody knew how to measure the MPI level performance. And that's what OMB we introduced, and over the years it has become like an industry standard. People are using it for procurement. Any paper you see about MPI, people use this OMB. So this is kind of as you can see, like the continuous download increasing over the years. So this is actually our software architecture. So if you take a look at the left-hand side is the networking technologies, the right-hand side is the CPU, GPU, DPU. And we started with the MPI. For some years also we expanded. Around 10 years back, there was a lot of interest in PGAS. We still have those solutions. But recently we have expanded not only from HPC, but deep learning, machine learning, and big data, data science. I'll go into details. But this is where our core research lies. In the group, every time a new networking technology comes, or a CPU or GPU technology comes, my students and all, we jump into saying, well, what is this new feature? How do you really take advantage of this? We write papers. And once the papers get published, in 3 to 6 months, we actually take it into the production. Okay? So in my lab, we have a lot of software engineers who work together with the students, and we have almost 200 servers running continuous testing, QA testing, and we make this code production ready, and then we make a release. Many of you might be on our mailing list, so you come to know about it and download, and then just it runs. So traditionally, we started with this HPC focus, like the MIP's library, if it supports CPUs, GPUs, DPUs, and interconnect. But then, since now we are entering into the AI and then to the big data, so we started asking the question, can we use that MPI library itself for the scale up and scale out? And if we can do that, we'll be able to deliver good scaling and performance portability. But more important is that vendor neutrality. Okay? That is my core thing here. If you take a look at it here, I've given some very quick equations. If you see how the commodity clusters are growing, CPU broadly 3 types. All right? Intel, x86, AMD, x86, and then ARM. Interconnects 4 of these. Let's say InfiniBand, Slingshot, Rocky, and OmniPath. The major ones I'm saying. There are other combinations. The GPUs 3. NVIDIA, AMD, and then Intel. So if you do a quick math, there are 36 combinations. People are deploying any one of these 36. Okay? So now if you see from a particular vendor perspective, again, no offense, I know there are several vendors here. So the vendors are actually delivering one combination of these. And this is where they optimize. Okay? Now you just deviate as an end customer if you want to know not that GPU, but I want this GPU, or not that interconnect, I have this interconnect, everything fails. All those optimization fails. So this is where we are trying to position ourselves, saying if you do go for like an API-driven solution, it will be vendor neutral, and I'll show you some of the performance numbers. You can actually get better than what the vendor is providing. And at the same time, we also want to take the Synthemavich MPI, or in fact, many other MPI libraries. Whenever some new technologies come, there is MPI libraries go and they try to optimize. We are always on the front, and we try to provide it also not only on premise but also on the cloud. So this is our latest release. If some of you are not, we have a something called MVPich Plus, which is like an advanced version. There is an MVPich which is the base version, then MVPich Plus, and this MVPich Plus was built on two different releases. Some of you might be familiar, like there was a GPU Direct RDMA release, MVPich GDR, and there was an MVPich X. So we combined it and then push it into this Plus, and that is our new series as we move forward. That has all the latest and greatest. It has all the support. And then what I'll be talking, there is something like I'll introduce this on-the-fly compression shortly, but these are our additional modules. So you have the MVPich module, then we have an MPI for DL module, MPI for QML module, MPI for Spark, MPI for Dask. So you can actually all this download and build your system. Okay? And then you have actually best performance for not only for HPC jobs or AI jobs, big data jobs, or any combination of those. Okay? So that your end workflow actually gets the best performance. So let me show you some sample performance numbers. I just chose 3 machines here. Okay? The first one is Frontier, which is the number 1 in the world, which is running at Oak Ridge National Lab. And a version, I think the Livermore National Lab is coming up with the El Capitan. They have a smaller version which is called Tioga. I'll show you some numbers. And I'll try to show you, in most of my presentation you have seen, there is a lot of graphs. I really go into very concrete numbers. I'll show some trends, but I'll share the slides so you can always digest those things later on. And then the second one is actually here in UK, iShambad AI. So thanks to Sadaf, Simon and all. So we have actually been working with them for the last few months, and we actually gave them a code drop. And I'll show you some numbers. And then the third one is like the Stampede 3 at the Texas Advanced Computing Center. So here you can see again this combination. So there is the AMD Frontier is AMD CPU, AMD GPU, Slingshot. This is Grace CPU, Hopper GPU, and then Slingshot. This is the Intel Sapphire Rapids, Intel GPU, and kernels network. So you can see all these combinations I told you. Like out of those 36 combinations, these are 3 combinations. Okay, and this machine, I know Paul is sitting here. This is like coming very close to your Dawn system. So look at the first one. Okay, so this is like on the Frontier, which is the number 1 system. It's actually the vendor is Cray. So the Cray MPich is that the default version, and you can see actually a MVPich bits Cray MPich. Okay, these are all the different OMB metrics. You can actually see these like a latency. These are the unidirectional bandwidth. Continuously, we are able to optimize it for all different message sizes, PPN sizes. So these are the CPU numbers. And then, of course, the collectives. As you know, the collectives are gaining a lot of importance, not just for HPC, but also for AI. If you do any training, the bottommost is like all reduce scatter, alt-wall. These are being used as if like the AI community is rediscovering these collectives. But the collectives have been there in the HPC world for many years. So here again, you see very similar kind of things. We are able to give like a 24%, 15%, depending on the collectives. So then if you go into the GPU West, so this is where many years back, we actually introduced, some of you must be knowing, called GPU Direct RDMA. How many of you have heard of that? GDR. Okay, several of you. We worked actually with Mellanox that time, and NVIDIA. They were separate companies, and OSU. We worked with also Sadaf that time, bringing this GDR, so that you can actually transfer data from GPU over InfiniBand over the network to another GPU. You don't have to go through CPU. So all those advanced designs we have been continuing, and this is where you will see again on the Frontier compared to Cray MPich, like these are like we are able to give like almost 62%, 68% benefit for all the different collectives. So then if you go to isomer board, so this is here like again a Grace and Hopper and the slingshot. Look at the numbers. It is very recent numbers. These were just taken last week, and we had a long discussion with Saraf's team and all. So they're trying to actually read on it. We give them a code drop. We ask them how to run it. So here you will see, like compared to Cray and Pitch, we are able to this the intra-node CPU latency that is all running on the Grace. And similarly, like for large messages, 22%, we can actually push the bandwidth by almost like a 47%, sometimes even 200% kind of things. Now, if you go to the GPU, and these are the actual numbers, for very short messages, we are able to deliver you like this intranode, like two GPUs sitting next to each other. We can actually transfer data in 3.5 microseconds. Okay, this is where that GDR and all are coming in, but Cray and Pitch is remaining at like a 15 microseconds. Okay, and then of course all the internode also for very large messages. Here you can see like we are able to give almost like a 38% benefits. Okay, so and then if you continue, these are the collectives. This is like a 55% benefits here. These are all reduced. The same thing here also all reduced like a 62%. Okay, so these are some of the sample numbers. Again, you can see if you are using Azure AI instead of using Cray and Pitch, we use our MRPitch deployment. Suddenly you will get a boost in your performance. Okay, and that's what I'm trying to say. Like if you design your MPI library properly, irrespective of the vendors, okay, you will be able to get a big boost in the performance. And this is actually application. That is a micro benchmark. So this application is called Hefty. Some of you must be familiar. This came from the Oak Ridge National Lab, the next generation FFT, and it is very all-to-all intensive. And this is on Eisenhower AI. We ran it here, like this is like a 32 GPUs, these 16 GPUs. At an application level, we are able to boost the performance by 1.3 or 1.76x. Okay. Now moving into the Sapphire Rapids and the kernel network, this is the Stampede 3 and similar things. You can actually run it on Dawn. The CPU side, this we are comparing again. This is an Intel system, so Intel MPI is the baseline. So here you can see like we are able to, depending on the message sizes, 1.81, 1.52, we are able to give the benefits. Now if you go to the GPUs, this is where these are very latest results actually. So this is what I was telling Paul, look at it, compared to the very latest Intel MPI with their SQL designs and all. This is like a we are able to like all reduce, which is very important, you know, for HPC and also AI application. 56x within one node, two nodes, 10 times, 15 times, we are able to give these benefits. And later on, I'll try to show these kind of benefits is boosting the AI training performance. Okay, I have another slide here. The same thing also you will see for other collectives. These are reduce scatter, reduce block, very similar train. Okay, these are very new kinds of design. We had these designs for NVIDIA GPUs, but the first time we were trying to bring it to the Intel GPUs. That's why you see very, very big boost in the performance. So then we are also working on the Bluefield 2, Bluefield 3. I think here I have presented many times earlier. If some of you are familiar with these architectures, so I call it like an executive and assistant. Okay, so if you think of your host processors or executives, the Bluefield 2 and 3 gives the ARM cores in addition to the RDM engine. So you can think of like these are assistants and these are the executives. So just like in the real world, you try to offload things to the assistants. We are trying to take similar kind of design within MPI library. Okay, and of course the first generation solutions we had like offloading non-blocking collectives, and this is actually a product. MRPitch to DPU. We are working with a startup called Xcel Solutions. This is a very complete product. I think I've shown some numbers earlier. You can get a boost in performance, 24%, 30% things. But some of these are very latest results. Okay, so I don't want to show those last results. So this is actually PETC. PETC library is like a numerical simulation library from Argonne, and that is very extensively used in a lot of simulation, like the OpenFOAM and all. And so what we have done is, earlier we had only non-blocking collectives we had uploaded. Now we have gone into point-to-point. So point-to-point non-blocking also you can offload, and then actually you can see the application level, we can give you like a 24% benefits at the PETC layer. Okay, so then if some application is running using PETC, you will see similar kind of boost in the performance. These are very latest. We just got last week, this paper got accepted at the IPC 2024 in December. So what we have done is the one-sided communication. Okay, everybody is working in the community to upload two-sided communication. So these are the one-sided communication. MPI put get open SMAN. So here again, you see very similar kind of things. We have done like not only we have offloaded the basic things, we have also like the kernels, which is running on top of that, like a block sparse matrix multiplication. We are trying to run that, and then we get here you will see this is like a blocking, non-blocking. If you do offload, you get very significant boost in the performance. This is also another paper. The same conference got accepted. This is very nice. Computation we have started offloading, not just communication. But the computation, people are trying to do blind offload. Okay? But if you know, these ARM cores are not very strong. So if I totally offload everything, then it slows down. So what we have done is something like a smart offload, or you can think of a hybrid offload. Okay? So just think of an executive. You are an executive and there is a secretary. Let's say some deadline is coming. You have to come up with some good plan that both of you work together to meet that deadline. So similar kind of approach we are taking. So if you see here, like this is Sapphire Rapids. So what we are trying to do, these actually these kind of operations are very common. Vector multiply, distributed dot, these kind of solutions or the applications. What we are trying to do, like a 96 process on the host and 16 on the DPU. So they are actually working together. Okay, even though DPUs are slow, these are fast. We are trying to balance the computation. If you're just the ARM cores, you completely offload, it takes more time, then you don't get the benefit. If you run everything on the CPU, many times if you're an executive, you say, no, I don't want to offload this to my assistant, I'll do it myself. But you are bringing more burden on you. So how do you really balance the workload? So that is the kind of things what we have done. And then here you see up to like a 24%, 15% improvement. These are very latest results. They are not available as a product yet, but we'll be trying to push it. These are the initial results. So with this, let me go into these are some of the HPC side, but now let me go into that convergent software stack onto the AI and big data. So this is where what we have done is we have several of such modules which are available. I'll just talk about a few of those. So first I'll go into this distributed training, how we have actually linked the AI workload, and then I'll try to show some results with Intel GPUs. Then this is a very new concept we have introduced for the last few years. It's called on-the-fly compression, then some topology of partitioning. And then I think this is something new which is coming, hyperparameter optimizations. People many times just do the distributed training. They don't go for hyperparameter training. Optimization, if you do that, you will again get a very boost in the performance. So what we have done here, I'm sure many of you have run PyTorch or TensorFlow, right? If you run any you go below, there are intermediate middleware like a torch distributed or deep speed or Horoword. These are the intermediate layers. And these layers, traditionally, like when NVIDIA says, okay, use nickel. So what they have done is they link to the nickel layer. Okay, if you go inside the code, nickel or RICL or XCCL, they do that. So what we did that, you modify that layers with few lines of code, we put it into our MPI layer. That's all. Okay, and we have actually made this code available in the GitHub. You can go and download it. And if you are a very good programmer, kind of a 1 hour or 15 minutes, 30 minutes, depending on your knowledge, you should be able to patch that. Okay, so all those communication, instead of going through nickel or RICL or XCCL, will go through MPI. That's all you need. You don't need anything else. Upper level applications will run, and you will get a boost in the performance. Okay, and that's what we have done. So we have been advertising these. These are like the MPI-driven solutions for AI. Okay. So now these are the things I showed, like an Intel GPU. We optimized all reduce. Those are like the all reduce level collectives. But now if you see the actual running, this is a PyTorch plus Horoword. We are trying to run the training. So now you can see I can give you, depending on the different batch sizes, system sizes, I can give you a boost in performance, 41%, 28%. Okay, because those all reduce were implemented very efficiently. If you just use the standard XCCL, you will not get this kind of boost. Okay, so we are going very systematic approach in collective optimization, and then go into the next level. So this is something new we introduced called on-the-fly compression. We introduced this 3 years back. We had a paper in the best paper finalists in IPDPS 2021. So if you think all these GPUs have a lot of cores. of course, you do use it for computation, but when you start communicating, these cores are sitting idle. Okay? So we thought, saying, okay, if I have a large data to send, which is very common in the AI workload, let's say I have 32 gigabytes of data to send, all those SGD, gradients and all, instead of sending it in the current version, can I actually do compression? Because the cores are sitting idle. I do a compression with a hope that the data will get reduced, and that's what happens. And then the other end, I'll try to do the decompression. But since my message sizes have reduced, I'll get a boost in the performance. That is the whole idea. Okay? And this is getting very traction, and that's what we've been doing. So here you'll see, like I just saw two sample results. This is a PSDNS, which is like a fluid dynamics simulation. Low is better. I can give you like a 64 GPUs. I can boost the performance by 30%. Just using this. And these are all available in our library. You just turn on the flag, and then you see the boost in the performance. And the right-hand side is actually, we are working with Microsoft. They work heavily on deep speed. So they're actually using UNOPs there, and then see with the compression 35% benefits. Okay? So this is something very new. Again, this just got accepted. This is actually running Frontier. You will see that whenever you hear about like Microsoft, all this training takes 6 months and all, there is a lot of things what we used to do in HPC, like mapping, scheduling, everything has to be rethought out here. Okay, and that's what we have done. Like this is a LLM training. So you need to see, okay, where to use all gather, where to use reduce scatter, where to use the optimizer, how to do quantization. If you do it properly, here you will see like a very big boost in the performance on the same hardware. We're not changing anything through the software. We're able to give like a 70% or 60% boost in the performance. So then this is the hyperparameter optimization. If some of you know, do people know what hyperparameter means? Like I have a training, all those different weights and all those things. During the training, you modify, but sometimes it starts with some basic parameters. But you are not very sure whether that is converging your solution or not. So there are new schemes where you can do this hyperparameter optimization. It is very expensive. But if you do it right, so we have introduced something called a HyperSAT, a distributed HPO framework. And if you use that, you can actually boost your training performance by almost factor of 3 or 4 kind of thing. So these are very latest things. All these are MPI-based solutions you can actually try to use. And then, of course, there is a lot of focus is taking place on inferencing. Now, people have got a good handle on training, but inferencing, think of like a ChatGPT. I'm sure many of you would have requested ChatGPT. Look at the server side. It is getting millions of such requests. Okay, so when you run ChatGPT, you will be seeing like a blink, blink, blink. After some time, your response comes back. So think of that the other end server, they are getting hit with all these things. How you do scheduling of these requests, because they have to match with your models and the layer. So this is where we introduce something called a proposed temporal fusion technique, because these are all GPUs, you have to bring the GPU kernels appropriately. And in the end, we're able to show, like if you see the GPT, Llama, all these things, we're able to push like a 16.7x benefits in the average parallel inference. So we are trying to utilize a lot of knowledge from our scheduling literature in the past, whatever people had done. So then let me go into the final part, which is like the same thing we want to do in the big data. So what we have done here is 2 parts, like MPI for Spark and MPI for Dask. So here what we did, in fact, in my group, some of you are familiar, we had a project called High Performance Big Data. We started in 2010. We had actually taken Hadoop over InfiniBand, Spark over InfiniBand. We were able to give a very big boost in the performance. But then, let's say Slingshot has come, Rocky has come. There is no fun in redesigning that, okay? Because it's exactly more like an engineering kind of thing. So what we did is, because our MPI layer is giving very good performance, we linked everything to the MPI layer. So now if MPI runs on any network or any CPU, GPU, Spark will run. Okay, so that is the whole motivation of this vendor neutrality and portability. So that's what I'm trying to show with the very latest MRPs Plus, what I showed here. So there are 3 bars here. So if you will see that this is the standard regular Spark. It is running over TCP/IP, over IP over IB. This is our actual high-BD designs, which we did like 5-6 years back. This is still older design, but if you see the latest MPI design has all the features, we are able to give you the best performance. Now, more interestingly, what happens, so this is like, let's say, InfiniBand, but now let's say this we ran on the tag. These are the Infiniment system, but this is a Stampede 2, which is a Omnipath system. So we didn't do anything for Omnipath. The stack just ran, okay, out of the box, because it is running over MPI. MPI runs, MRPC is running over, optimized for for OPX. It will just run. So any of the other stacks can run, so you get immediate boost in the performance. Same thing when run now on the Slingshot. So you don't have to redesign those stacks entirely. So you will get much more rapid production kind of things. You can give it to the end users. Final thing, I'll introduce the Dask. I think we heard today like the DDN talk, like the SCA project and all. I think this is where a lot of Dask is being used. So same thing we have done. In the Dask, we have linked through the MPI for Pi to our MRPs to GDR. And then this is like trying to show some QDF merge. And then here the same thing you'll see. This is IP over ID. This is UCX-based solution NVIDIA has been proposing. This is our MPI for Dask. You will see this is the left-hand side, lower is better. Right-hand side is the throughput, higher is better. Again, the same idea. We are trying to link it to the MPI layer so that if the MPI layer is designed properly, you will get a boost in the performance with the Dask. So with this, let me conclude here. So what I tried to show here, if you take a look at like an exascale systems, you need to design these things in a holistic manner, not just purely only MPI or only AI or cloud, but you need to take a look at that, and that's what in my group we have been doing for the last 30 years. And I presented some of the results, how you can design this in a vendor-neutral manner, and show some of the solutions. And this is where we are talking to the next generation Zetascale systems. We need to move ahead. I just want to show this on the MRPs project. Some of you are familiar. We do an annual MRPs user group conference. We bring people from all over the world. You can see all these talks. Sadap actually gave a keynote talk. Go there. All the slides and videos are available. We did it in the last one. These are all our sponsors. Thanks to all of them, but these are all my heroes. Okay. Whatever I presented in 30 minutes is a work of almost like 100 people over the last 25 years. So with that, I'll conclude here. Thank you. If there are any quick questions, I'll be happy to answer. Otherwise, I'm here until tomorrow. We'll be happy to talk. Thank you.
Thank you, DK. Any quick question? Sir.
That was a brilliant talk. Thank you. So what has NVIDIA said? So I work with NVIDIA and have done some of these tests that you're talking about. What have they said, and what are they going to do about the fact that you're beating them in speed?
Yeah, I mean, so we still work with NVIDIA. So actually the parallel inferencing results, as soon as we publish the paper, you always get a request from some company like NVIDIA saying, we don't believe your results. That is the first thing. Okay? The standard response, again, no offense to anybody. But then we say, no, this is correct result. So we go back and forth, then they say, wow, this is a new solution. In the 2 months, they take it there. That's what has happened. So you take that tensor LLM, the latest inference engine, has our designs. Okay? Same thing happens every time. We have a paper, people say your numbers are not correct, but we stand with our results. And then people take, that's fine. And then we move ahead to the next design.
All right. Thank you, DK.
Thank you.